Hey everyone. Okay, so it's already 10 and I think we can get started. Okay, so first of all, I wish all of you had a nice Thanksgiving break. I hope that you're not working on the team project when you're working on the when you're eating turkeys. Okay, so I know that the team project actually needs quite a lot of efforts. It is a teamwork, really. So and also the calculations, they are a little bit more sophisticated than what we have gone through in the classes. But still, we have 1 week left. So if you have any questions, I think it's a good time that you can get on full speed on the project. And also, please bear in mind that we also have the extra office hour on Tuesday. So this time I'll probably be a little bit late on Tuesday night. So maybe I'll be there at 7:30, just half hour later than the original time. Okay, so if you have any questions, you can come to the office hour. And also we have office hour on Wednesday morning from 9 to 10. And if you notice on the syllabus, so based on the class schedule, we don't have a class on Friday, but I can make it, let's say, similar to the Zoom lectures that we're having right now. So if anyone has any questions, you can join. But if you don't have any questions on the team project, you can just skip that class. Okay, on Friday, I'll be there too. So it is a little bit unfortunate that I couldn't be there today because my flight got canceled yesterday. So I guess that's what happens when people travel during the Thanksgiving. So I'll try my luck again this afternoon, actually in 3 hours. So hopefully I can catch it and I'll be in the class on Wednesday. One last thing is about the course evaluation. So this morning, the course evaluation is officially available. So as you can tell, I'm also quite new to the department. I think I joined the department the same time compared to many of you guys. So so that's why the department also wants to collect your feedback, comments, suggestions on this class so that I can further develop this to make it more fun, to make it more relevant to what you need. So if you, let's say, I think generally you would have time to do these evaluations. So I would really appreciate your comments, suggestions, and I promise that if we got more than 50%, let's say completion rate on the course evaluation, I'll bring pizza and soft drink to our presentations. Okay, so next Wednesday, if I know that. So that the course evaluation, so more than 50% of you guys completed the course evaluation, I'll bring the food to the class. Okay, so this class, I would say that the contents of this week is going to be less relevant to air pollution. It's more on meteorology or atmospheric science. So it's a different aspect of the knowledge. So there's more, I would say, general concepts instead of calculations there. So this class, we're going to just focus on the meteorology, okay? So I think we spent a lot of the time talking about different types of air pollutants, how they're being generated, what are the reactions, and how do we control them. But it is one thing to think about how they're being generated, but it's equally, I would say it's equally important to consider their transport. Because let's say that if all of these polluting industries or power plants, they're just located nearby the coast area and the wind is just blowing all of these pollutants over the ocean, then people will probably be less concerned about these pollutants, right? So they're not floating over to my backyard. So why do I Why do I care about that, right? It's not affecting my health. But it is not the case. So actually, the wind direction is going to disperse these pollutants, right, to all the directions. So that's why we have to know what's going on in terms of the meteorology, to know what are the general wind patterns and how we can better design, how we can better think about the locations or the sites for these industrial plants, okay? So talking about the wind patterns, I would first like to share with you a video about the transport of aerosols. So this is a video that's taken by the satellite. It's actually a NASA satellite that's just designed to monitor the transport of aerosols. So let me just start sharing this video here. Okay. So this is a NASA satellite that's trying to map out what are the transport pattern of the aerosols. So you can see from the top left, so this is actually taken 2006, and it's changing by each day, right? So right now it's in September. So on this video here, you can see, or this recording here, you can see a lot of transport of these dots here. So these are actually the aerosols. So the satellite can also tell us what types are these aerosols. For example, you can have the red ones, which are the dust. It's quite obvious that there's quite a lot of dust that's transporting out of the Saharan desert, right? And so you can also have the organics and black carbon, so they're in the green. So generally the organics are coming out of the forest, right? So you can see that forest, for example, the Amazon forest in the Siberia, right? There are some organics getting emitted. The white ones are sulfates. So those are generally correlated with the places that has a lot of sulfur dioxide emission, right? So it's related to the industries. So that's why over the East Asia, right, over the United States, you can see these white aerosols getting generated and dispersed. You can also have the sea salt. So sea salt are over the ocean, right? So just by looking at these transport patterns, you can see that there are general directions for these aerosols to transport that's caused by the wind, right? For example, near the equator region, right now here, this is the equator. You can see that the dust is generally transporting from the east to the west, right? It's getting out of the mainland of the Africa. And same thing for the forest region, right? So it's transporting from the east to the west. So what about over the United States? So I'm just going to pull out a quick quiz just to make sure that you guys are watching the video. So what is the general wind direction over the United States? Is it east to the west or west to the east? I think it's pretty obvious here, right? So 5 more seconds. Okay, we'll stop here. So most of you guys made the correct choice. So that's from the west to the east, right? So the wind is blowing from the west to the east. So this is going to be quite convenient when people are trying to find sites for the polluting industries, right? So we could just distribute them over the East Coast. So that's going to be a little bit more convenient when we're trying to emit all of these pollutants, right? So they're just going to get dispersed over the ocean, and over the ocean, since no one's living there, and also there are, let's say, precipitations or rainfalls that are removing these particles, so we can be less concerned about it, right? So, well, we see these types of phenomena here, but why is that the case, right? What is generating this special types of wind patterns? So as we said, over the equator region is from the east to the west, and then over the United States, or more generally over the mid-latitude, is from the west to the east. But if you further look at the polar region, so actually the polar region is reversed again, is from the east to the west again. So the similar phenomena is happening over the southern hemisphere. So for the southern hemisphere, near the equator region, let me just go back. So near the equator region is from the east to the west, and then in the mid-latitude is west to the east, and then in the polar region is east to the west. Okay, so basically you have 6 different regions where the transport of where the wind directions are quite different to each other, right? So let me share back my screen. Okay, so why do we have these different types of wind directions? As we said, over the mid-latitude, it's in this direction, right? The higher latitude, it's this direction. Equator region is here, right? Similarly, for the southern hemisphere, you have that, and then you have this thing, right? So what is creating this types of wind circulations? So to understand that, we have to know what is creating the wind. So a simple example can be, let's say we blow the air out of our mouth, right? So we basically create a pressure difference. So it is because the air that's in our mouth has a larger pressure compared to the ambient environment. So that's why it's getting out. It is the same case on our Earth, but it is using a different types of mechanism to generate this wind that is caused by the temperature difference. So we know that according to the ideal gas law, that's PV equal to nRT, right? You can know that generally the higher the temperature, the lower the density, right? So the density is just basically the M multiplied by the molecular weight. You're going to get M and then divide that by V, right? So you can see that basically for this ideal gas law, you could get a rho multiplied by T, and then on the left-hand side, it's just going to be P multiplied by the molecular weight divided by R, right? So basically, you are going to get a inverse correlation between the density and the temperature. So that's why if you have a higher temperature, the air density is going to get lower. So what that means is that the air is going to rise up, right? So if you have a hotter air, then they're going to rise up. Let's say that this is our ground, right? And for some reason, this region has a higher temperature, then the air is going to rise up. So when the air rises up, you create a lower pressure at this location, right? So that's why the cooler air from the outside is going to try to fill in the gap that's left by the hotter air, right? So this is going to be hot, this is going to be cool. So this is exactly the same mechanism that's creating the wind on our Earth, right? So in order to create the wind, we need to have a temperature difference. And it is not surprising that we have temperature difference on our Earth, right? So the tropical region are generally hotter compared to the polar region. So the reason is because of the sun, right? The solar radiation. Because compared to the size of the Earth, we know that the sun is much larger, right? So if I just draw out part of the sun, it can be probably this big, right? It's very large compared to the Earth. So that's why we can assume that all of the radiation that's coming or that's going towards the Earth are parallel to each other. So you're going to have these solar radiation that's going this way, right? And now if you just take the same kinds of distance or the same kinds of or a same gap over the equator region and over the polar region. So we know that for these two different sections, they're receiving the same amount of solar radiation, right? But the difference is that over the equator region, you're looking at a smaller land surface. But over the polar region, you're looking at a much larger land surface. So the land surface is much larger, right? So that's why the temperature over the polar region is going to be cooler, because you have to distribute all of these heat over a large land area. But over the equator region, you have a smaller land area, the temperature is going to be higher. So as we introduced here, the temperature is higher, right? The air is going to rise up, right? So the air is rising up, and the cooler air is going to try to fill in the gap that's left by the hot air. And because of that, you have to force a circulation of the air, right? Because of the mass balance. So you're going to form this type of air circulation. So the cooler air is going to arrive from the polar region towards the equator region, and hotter air is going to rise up near the equator region and then go back to the polar region. So this is the general wind cycle that's happening on a, let's say, a spherical object. The reason why I say that it's a spherical object, but not the Earth, is that our Earth is so big, right? Compared to the sun, of course, it's very small, but in terms of its actual diameter, it's still very large. So that's why there's no way that we can sustain this type of large recirculation of the air. So what happens instead is that we're not going to have this one single cycle here. We're going to break it down into multiple cycles, actually into 3 different cells. So if you still remember what's going on here, right? Over the equator region, the warmer air will rise up, right? And then cooler air will get in. So we'll first form a circle or a cycle that's over the equator region. So you're going to form basically a smaller cell of the air recirculation. And in terms of the polar region, it's the same, right? You have the cooler air settling down. It's going to reach out, right? Going to the southern part, right? And then rise up and then go back. So basically these 2 cells or these 2 recirculations are the same. They're using the same direction. But it is what's happening in the mid-latitude is a little bit surprising. So what happens is that this recirculation is reversed. It is reversed mainly because they're being forced by these 2 cycles, okay? So both of these cycles are going this way. And then in the mid-latitude, what happens is that it's going to use this type of recirculation, okay? So that's forced by the wind direction at here, and then forced by the wind direction at here. So we're going to have basically a reversed direction of the recirculation, okay? So basically, this is because the dimension of our Earth, right? So the air recirculation is broken into 3 different cells. It is the same case for the Southern Hemisphere. So in the Southern Hemisphere, you also have this recirculation near the equator region, right? It's going this way, right? And then over the polar region, you have it going this way. And then in the mid-latitude, it's forced to have a recirculation that looks like this, okay? So that's why when we talk about the air recirculation on our Earth, we're going to divide them into 6 different cells, right? You see that you have 1, 2, 3, 4, 5, 6. Okay, so if you imagine, or if you think back on the wind directions here, we also labeled 6 different directions. So it's basically representing the air direction or the wind direction in 6 different cells of the air recirculation, okay? So actually people give names for these different cells. So we could have the tropical cells, that's called the Hadley cell. So in the northern and southern hemisphere, we're going to have 2 Hadley cells, right? And we're going to have 2 polar cells, right? These 2 cells are having the same direction in terms of the wind recirculation. And then we also have the Ferrel cell, that's in the mid-latitude, right? You can see that the United States is located in the Ferrel cell, right? So now if you look at the wind directions in these cells, basically we just talk about what is the wind direction from north to south or from south to north, right? So for example, in the Hadley cell, right? We know that in the Hadley cell near the equator region, the wind should be blowing from the north to the south, right? In the polar region, it's the same, north to the south. And then in the mid-latitude, it should be going from the south to the north. But what about the east and west wind directions? Because when we look at this video here, it's giving us the east to the west or west to the east types of wind direction, right? Not the, I would say the northeast or the north-south types of wind direction. So to understand that type of wind direction, we have to know the Coriolis force. I think you guys probably have heard of this Coriolis force or the Coriolis effect in high school. So it's a little bit complicated to prove that in physics, but I would say an easier way to understand this is just to imagine if we're trying to throw out a dart or trying to shoot a bullet over the polar region or at the equator, okay? So for example, we're trying to shoot out a dart at the North Pole or near to the North Pole, right? And then since we're shooting the dart out at this very north point, right? So no matter which direction we're throwing the dart, it's always going towards the south. Okay, so for example, we're trying to shoot this dart towards the city at the equator. That's Quito, right? It's a city in Chile. So when we're aiming our dart towards this city here, one thing we need to know is that we only provide this dart with a velocity from the north to the south, right? We didn't provide any velocity in the east to the west or the west to the east direction. Okay, so this velocity is going to be 0. Well, we have a, let's say, a velocity larger than 0 in the north to south direction. Okay, but we know that when the dart is out, our Earth is rotating. So our Earth is always rotating from the west to the east, right? It's rotating towards this direction. So that's why when the dart is flying out, and then if you compare the dart's velocity to the velocity of the land, let's say when it passed to the over the United States, we know that the land is flying or going with a speed that's going from west to the east, right? But the dart doesn't have any of that velocity. So what that means is that the dart is going to start to divert towards the right, okay? Because the speed of the dart cannot catch up with the land speed in terms of the west to the east direction. So that's why the dart is going to get diverted, and then until it's completely off the target. So basically the dart is going to divert to the right. Okay, so it is the same case when we're trying to throw out the dart on the equator. For example, we are just sitting at Quito here, right? And then trying to throw a dart directly towards the North Pole, right? Although we were aiming it towards the very north, but we know that the dart is also going to carry a, let's say, a velocity from the west to east. And actually, since it's located at the equator, so this velocity is going to be very large, right? So when the dart flies out, so if you compare the dart's velocity from the west to east, let's say the dart. So this velocity is going to be much larger compared to the land velocity. Okay, or the surface velocity, because here, I mean, at the equator you're basically at the location that has the largest diameter, right? And when you're talking about the, let's say over the United States, right, the diameter is getting smaller. So that's why the land velocity also gets smaller. So basically, when the dart flies to here, it's going to carry a much larger velocity from the west to east compared to the land beneath it, right? So that's why the dart is going to divert towards the right, and then go this way. So it's going to go completely off the target. All right. So for both of these two directions, let's say in the northern hemisphere, if you're trying to throw the dart out, they're eventually going to divert to the right. If you're looking at the northern hemisphere, it is the same case for the wind. Let's say that the wind is trying to blow from the tropical region towards the mid-latitude, right? If it's trying to blow this way, it's never going to follow this straight south to north direction. It's always going to divert to the right. Okay, it's the same case for the North Pole. It's going to divert to the right. So we talk about the northern hemisphere. So what about the southern hemisphere? It is going to be quite similar, right? So if we have the Earth here, we know that, let's say, if we're sitting at the Saharan desert, right? And then we're trying to throw the dart towards the North Pole and South Pole, right? And we know that basically, since at this location, you're going to have the largest speed from the west to the east, eventually you're going to have the dart divert to the right. And then similarly, the dart shooting towards the southern hemisphere is going to divert to the left because you have a larger line speed, larger velocity of the dart, right? So that's why when we talk about the northern hemisphere, we say that it's going to divert to the right. And when we talk about the southern hemisphere, actually it's going to divert to the left. Okay, so actually quite a few of you are in my 2601 class, and I said that there's actually an easier way to memorize this. So we'll say that because we're living on the northern hemisphere, we're always right, okay? So it doesn't mean that people on the southern hemisphere are wrong. So it's just they're diverting towards the left, okay? So hopefully that's gonna be a little bit easier for you to memorize this, but just to think about the wind directions, right? Whenever they're trying to flow from the north or flow from the south, if we're located at the northern hemisphere, the wind direction is going to get diverted to the right. So now let's look at the air recirculations. Okay, so we said that in the Hadley cell, right? So near the equators, over the tropical region, the wind is going to blow from the north to the south, right? And now since you have the Coriolis force, the wind is going to divert to the right. And that's why you have the wind going this way. Okay, divert to the right. So in the northern, in the mid-latitude, right, over the United States, we know that the wind is going from the south to the north. But because of the Coriolis force, it's going to divert the wind direction. Okay, it's going to go from the west to the east. Okay, so that's why if you go back to the wind patterns here, you can see that over the United States or over the mid-latitude, actually the wind is always going from the west to the east, right? And then in the equator region is from the east to the west. Right, so that's caused by the Coriolis force. And one more thing that I want to point out is that actually for this air recirculation here, the air is not recirculating, or the air is not reaching, let's say, even outside the Earth's atmosphere. Okay, so there's actually a height that the air cannot further rise up. Okay, so this height here, or basically this boundary here, of these Earth air recirculation is called the Tropopause. Okay, so everything below the Tropopause is called the troposphere. So if you recall, for the ozone, right, we said that the tropospheric ozone is a air pollutant, is a criteria air pollutant, but the ozone that's in the stratosphere, the ozone in the stratosphere is actually beneficial to human beings, right? So basically, what that means is that if the ozone is inside the, or is below the tropopause, right? And you see that there's air recirculation, so it can get transported everywhere. It can go to the land surface, right? So that's going to damage humans' health. But if it's in the stratosphere, which is the layer of the air outside this troposphere, right? So these ozone are going to be actually good ozone molecules that's protecting the human being and all different types of animals. Okay, so there's a height for this troposphere or the tropopause. So near the tropical region, this tropopause is going to have a height of, let's say, around 15 kilometers. This is actually very high. Okay, and near the I would say near the polar region, this height is going to be much lower. It's around 8 kilometers. So this is mainly because over the tropical region, the temperature is much hotter, right? So basically the air can rise up for a much larger, much higher extent. Okay, so in this way, the troposphere is going to be higher near the equator region. Okay, so this is about the general air recirculations. Now, if we go back to the question, right? So where should we build all of these polluting industries over the United States? Now you can imagine that if we just put them right here, then we can probably be less concerned about the air pollutants, right? Because it's going to be quite challenging for these air pollutants to go back to the land or to the continent. But if you're building them near the West Coast, then we may have a problem, right? So the air pollutants can get trapped in there. So this is one, I would say this is one application of the Coriolis Force. So there are a few other pretty interesting applications. Okay, so one of them is about the directions or the rotation of these hurricanes, right? So every year we will hear some news about the hurricanes, right? So getting generated from the tropical region, and then they're most likely they are going to land, I would say, near the Florida or near the Texas region, right? So these, I would say these hurricanes are basically, it's a recirculation of the air, all right? So what happens is that if you think about, let's say, near the ocean surface, you're also going to have some locations that are warmer, some locations that are cooler, right? So according to the ideal gas law, so the warmer region, the air is going to rise up, right? And then the cooler air is going to try to fill in the gap that's left by these warmer air. So in general, you're going to have a lower pressure, let's say a low pressure center, and then nearby it, these are going to be high pressure regions. Okay, so the reason why you can see a lot of clouds over here is actually because we're at the ocean, right? Where the ocean has a lot of water vapor. So as the water vapor rise up, we know that it's going to condense, right? So that's why you're going to form clouds over this region here. Okay, and so this is a way to look at the hurricane, I would say, from the let's say from the side of it, right? But if you look at the hurricane from the top, if you have the top view, then what happens is that you are going to have a low pressure center, right? And then you're going to have high pressure nearby it. Okay, so what happens is that air is going to get, I would say, get attracted towards the low pressure center, and then you're going to have these type of structures. But because of the Coriolis force again, we're going to see different types of recirculations of these air, right? So here I'm showing you two different types of, I would say the same type of hurricanes, but one is located in the northern hemisphere and one is located in the southern hemisphere. So based on the Coriolis force that we just introduced, right? So northern hemisphere is bending towards the right. Southern hemisphere is bending towards the left. So can you tell me which, I would say, which hemisphere is this first hurricane located at? So this is going to be the second pool. I'm going to launch. So it's asking which hemisphere is the first hurricane located at. Okay, 5 more seconds. All right, we'll stop here. All right. So I think we had a pretty tight competition here. But again, most of the people got the right answer. Okay, more than half got the right answer. It should be the Northern Hemisphere. So I think maybe for those who chose the Southern Hemisphere, you're probably misled by this arrow here. So maybe you're thinking that this is bending towards left. But when we consider this recirculation or this rotation here, we need to consider basically what type of rotation we're talking about, right? So let's say that right now we're in the Northern Hemisphere for this structure here, right? We're talking about this structure. So the wind, we know that the wind is going to blow towards the low pressure center, right? So since we're at the Northern Hemisphere, the wind is going to divert to the right. So instead of having this direct going to the center, you're going to have the wind that's diverted to the right. Okay, so basically you're going to have a counterclockwise. So you're going to have a counterclockwise type of rotation, right? So if you look at this rotation here, this is counterclockwise, right? So this should be Northern Hemisphere. So the reason why you have these bunted arrow here is because the air, it cannot fly by, or it cannot go by straight lines, right? So when the air really gets compressed, right? This is just not 4 directions. There are basically air from all directions. So they're going to compress each other. So that's why the air is going to get bent. And then that's why the basically you have the arrow that's a little bit bent, shown a little bit bent in here. But if you look at the direction, let's say either counterclockwise or clockwise, you can see that this is basically located at the Northern Hemisphere. Okay, so the similar case for the Southern Hemisphere, right? If you draw the low pressure center again, high pressure, high pressure, high pressure, high pressure. So we know that in the Southern Hemisphere, it's going to get bent towards the left. Okay, so you're going to have this type of rotation. So this is going to be clockwise. And then that's why this is located at the Southern Hemisphere, right? So this is what we can see in here. So I'm not making this up. So to show that, I think it will be quite interesting to track actually one hurricane. So I think probably in these 2 years, the hurricanes were not so strong. But in 2019, there was a very strong hurricane that's actually can be written in the history book. It's the Hurricane Dorian. It occurred in, actually it started in August 24th. So it was landing nearby the Florida region, and there was a lot of news, a lot of damage about this Hurricane Dorian as well. So here I'm just going to share with you the satellite images of these hurricane here. Okay, so if we come to here, so this is again the satellite images that's recorded by the NASA satellite. Okay, so if you recall the time, that was in 2019, right? And then it was August, I think it was August 24th. Okay, so right now it's showing the Africa region, but if we drag here, this is North America. So the Dorian is getting formed in here, okay? So it's still at its birth, right? And now let's try to track it. So you see it moved a little bit. Now we're at 25th, 26th, it's getting larger and larger right here, okay? 27th, 29th, 30th, 31st, September 1st, right? Size gets much larger. And now you see here, right? So its size is even larger than the state of Florida, right? You can see like a open hole in the center. Now, if you track its direction of the rotation, right? You see this is counterclockwise, right? It means that we're in the hemisphere, the northern hemisphere, right? But this is actually indeed a very strong hurricane that caused a lot of damage. And then let's try to track how it goes away, okay? So after it touched the land a little bit, right? And then it went this way and really fastly, just one day, it flew to the northeast and then got dissipated in the Northern Atlantic, okay? So it is also pretty interesting that you see once it touched the land, it's just following, it's just flowing from the west to the east, right? So the entire hurricane is also following the general wind pattern on our Earth, because we said that in the mid latitude, the general wind pattern is from the west to the east, right? So if you go back in time, right? So you see this is going from the west to the east and then got dissipated away, right? So this is the hurricane, or this system that we can apply our knowledge of the Coriolis force. So if you, let's say, go back to the contents. All right, so this is one application, and another pretty interesting application is the commercial air travel. So I'm not sure if you guys fly to the West Coast a lot, right? Or if you have taken flights towards the West Coast before. But generally, those flights are pretty long, right? It's like 4 to 5 hours. But I don't know if you noticed that the time for the direct flight, let's say from St. Louis to Seattle, if you're going from St. Louis to Seattle and from Seattle back to St. Louis, the time is pretty different. It's quite different, right? One is 4.5 hours and the other is within 4 hours, okay? So this is again because of the Coriolis force or the general wind patterns, okay? So we know that the wind over the United States is blowing from the west to the east, right? So basically, if we're trying to fly back from Seattle to St. Louis, right? From Seattle to St. Louis, so the travel time is going to be shorter. If you're flying from St. Louis to Seattle, right, the time is going to be longer. That is because you're flying basically against the wind. And for the other direction, for this direction here, the plane can just sit on the wind and then fly back, right? It's saving the fuel, and also you can enjoy a faster speed. So more, I would say more scientifically speaking, it is not caused, or this difference in the time is not caused by the surface wind, okay? So if you come back to here, so basically the wind directions that we're showing here, these are the surface wind. Okay, so more technically speaking, this is not, I mean, the commercial jets is not affected by the surface wind. It is caused by a special type of wind that's called the jet stream. So for those of you who are interested in this type of phenomena, you can search for this term here. So the jet stream is the types of wind that can basically create a very strong west to east direction types of wind. But that is also caused by the Coriolis force, okay? So it's still related to our Earth's general wind recirculation patterns in there. So every year, I would say especially during the winter time, you can hear a few news about the jet stream, right? So it's generally related to the cold air that's flowing from the North Pole, okay, from the northern part, and then meets with the warmer air, kinds of near the boundary between the United States and Canada. So this type of colder air, when it meets with the warmer air, is going to create a pretty strong types of jet stream. Okay, so whenever these type of weather conditions happen, actually the commercial airlines can enjoy even a faster types of flight. Okay, so basically you can create an even more, I would say, even larger time difference when you're trying to fly from either directions in there. Okay, so this is about the Coriolis Force and its applications. And at the end, I think we can talk about how these air pollutants can travel in the global scale. Okay, so we said that I would say in the different cells, right? In different cells, you can have air recirculations going on, right? So in the polar region, you have these types of cells, right? In the mid-latitude, in the tropical region, it's the same direction. And in the mid-latitude, it's something like this, okay? And we also show that in the mid-latitude, generally, it's the wind that's flowing from the west to the east. So that's why when you consider the transport or the dispersion of these air pollutants, it's going to be the fastest when you're talking about the transport within each single cell. Okay, so for example, this is the mid-latitude cell, right? So if you're trying to transport some air pollutants, right, from the United States to East Asia, you just need 2 weeks. So the same thing from East Asia to the United States, it needs around 2 weeks. So that's why I think in 2011, when Fukushima happened, right, people were concerned that those radioactive materials can get dispersed very fastly from Japan to the United States, and people were quite concerned about it. So generally, within each cell, the transport is going to be the fastest. But when you're talking about transport across different cells, right, from the mid-latitude to the tropical region or the mid-latitude towards the polar region, is going to be longer. Okay, it's going to take around 1 to 2 months. And it's going to take an even longer time when you're trying to go across the hemisphere. Okay, if you want something to transport from the northern hemisphere to the southern hemisphere, it's going to take almost a year. Okay, so that's why the transport of these air pollutants are going to be very efficient if you're talking about, let's say, over a country, right? So it's generally a much smaller length scale for the transport of these pollutants. So this is about the horizontal transport, right? So this is a horizontal. It means that it's just flying from north to east or west to north to south or west to east. So what about the vertical transport? So we know that this air can also go up, right? So we introduced the concept of the tropopause, right? We said that everything below the tropopause is called the stratosphere, is called the troposphere. And then everything between the stratosphere and between the stratopause and the tropopause, this is the stratosphere. Okay, so in general, if you want something to transport within the troposphere, it just takes around 1 month. Okay, so everything that we emit from the ground, right? Let's say the smoke that we generate from the barbecue, right? When it wants to reach to an altitude of 8 to 15 kilometers, right? It just needs 1 month. And actually, at the very bottom of the troposphere, there's a layer called the boundary layer. So the boundary layer is even thinner. It's between 1 to 3 kilometers. You just need 1 to 2 days to get it transported. But when you're trying to go across the troposphere and the stratosphere, or basically when you're trying to go across the tropopause, you're going to take a much longer time. It's going to be 5 to 10 years. So that's why people are concerned about the CFCs, because we know that the ozones are here, right? The CFCs are emitted from here. So we know that these are very efficient in destroying the ozone in the stratosphere. But basically the transport from the troposphere to the stratosphere is very slow. So maybe we haven't even reached the peak of the CFC concentration in the stratosphere yet, right? Although we already banned it in here, but it's still staying in the troposphere, and it's going to take a very long time for these CFCs to arrive at the stratosphere to further destroy the ozone. Okay, so this is about the different types of time scales for the transport. Okay, so that's it for this class. So next class, we're going to talk about more on the cloud formation and also the design for the stacks. Okay.